right, so we are going to do our problem set 4 solutions. So let's look at this diffusion couple. All right, I could already see which one is going to diffuse more. I know that my diffusivity of red is greater than my diffusivity of blue. So if I'm looking at fix, I'm going to have a flux of red going way here. So J flux of red in the C frame. My blue will go this way. My J of blue in the C frame, and my vacancies will move this way, J of vacancies. So vacancies are agglomerating over here, materials leaving this side, vacancies are flowing into here. So eventually, if I do have pores, they will form on this side. So I am destroying planes here, I'm adding planes here. So this material is going where? It's shrinking because I'm destroying planes. This material is adding planes, so it's expanding here. So where's the interface going to move? My vacancy or my interface, the fluxes are going to move in the same, or actually that interface is going to move in the same direction as the flux of vacancies. So I probably already answered a lot of those questions. You see I draw these all as the same magnitudes because I know that in my C frame, my flux of red plus my flux of blue plus my flux of vacancies must be equal to 0. So let's see what I did. Yep, answer this. Which material is smaller? So again, maybe my red is smaller. Maybe my solubility of red into blue is greater than blue into red. So those could all be answers. Explain qualitatively and quantitatively difference between intrinsic and self-diffusivity. So qualitatively, our self-diffusivity is just when we have one material that's diffusing. Our intrinsic diffusivity is given by, when we're connected to another material, like in this diffusion couple. And that is in the notes. You can look up that equation, a very, very nice equation. We did the flux in C frame. We wrote all the fluxes, described how you determined it. We talked about what will happen in the direction of my interface. How would you calculate the velocity of this interface? So I would look at the flux of that interface, or actually, I can say the velocity of the interface in the V frame. And that, again, is in the notes. You can look there. And then where will pores form? They will form on the right-hand side, the red side, as long as we have, what? Large enough temperatures and long enough times. So we must have that in order to work with this. So let's look at the next one. So I have a diffusion couple, and I connect a meter-long piece of, so this is a meter, of AU to meter-long piece of germanium, not to scale, but you get the picture. I can look at the diffusivities below here. So I need to solve the expression, plot the concentration plus function of difference in time for both materials. So the PDE that I'm going to solve is Fick's second law. So partial differential equation, dc dt equals basically d squared c dx squared. But I don't want to solve PDEs. I want to solve ODEs. So I'm going to introduce my variable eta, x over square root 4 dt. And my new equation is going to be d squared c d eta squared plus 2 eta dc d eta. So that equals 0. So I have my ODE now, ordinary differential equation. It's a derivative. Windows credentials, but I'm not going to give it to them because we need to solve these problems. So we've described ODE, we've defined it, differences, got the PDE. So now I need my boundary conditions. So if I'm looking at AU, I know that the concentration, I'm going to say that this right here, this is my x equals 0. This is x equals minus infinity. How do I make the semi-infinite assumption? Well, I'm going to assume that the length of my material that is diffusing through is greater than 10 square root t. So as long as that condition holds, I can make my semi-infinite approximation. So if I'm looking at the concentration of AU, I know that at an eta equals minus infinity, that's just going to be equal to 1. And then for here, eta equals infinity, that's going to be equal to 0. And you can get the similar expressions for GE as well. So GE, that eta equals minus infinity at 0, and then positive infinity here. But instead of writing it disgustingly like that, let's go ahead and do it right now in our Mathematica. So let's get Mathematica warmed up. Let's look at some values here. Am I given what temperature that we're at? Not really, but I think we just need to look at when our material, when is it valid? Actually, we can look at that in just a little bit. Actually, you see, we have germanium. Where's gold? I don't see gold in this plot. unless I'm missing something. I don't see gold in this plot. So anyways, but we are not even asked actually to really solve further. But anyways, certain materials below. Am I asked to write out? Actually, we just need the boundary conditions, initial conditions. So we've already set it up. In order to solve your differential equation, remember we just do dsolve. What is our differential equation? Well, it is, again, C is a function of eta. And I think you need to do eta double bracket, yes, plus 2 times eta times C is a concentration of eta, bracket, set equal to 0. And then our initial, let's see. Remember, I don't really solve differential equations too often because my research thankfully doesn't involve that. So I need my function, got it, y of x. Oh, I need to set my initial condition or my boundary condition. So now I'm going to set that for gold, for example, or actually let's do gold. So for gold, the way that I set up my problem, again, you could have different answers, but it just has to be consistent with your answer. So infinity, set that equal to 1. And so for C at minus infinity, I could set that equal to 0. And voila, now I need to do, again, C is a function of eta, and oops. Let's see, I probably messed up. So let's go look back at that help menu. Again, always nice to kind of see. So I've got my dsolve. I've got my, so I need to put those, that's where I was when I was typing this, I was worried about, can I do this? I need to type that right in the front. There we go. And voila, I've got my function. So I could plug that in. Again, I know that eta equals, x over root dt, so I could start to plot those out for those different values. So again, my solution is valid until this length greater than 10 root dt is, true. So really, until that, diffuses a meter. So for my length and d and t, so you can kind of figure that out. Great. Now I need to calculate the activation energy of Fe and vanadium. So I know a couple of things. I know, for example, that my diffusivity is equal to d naught exponential minus qa over kt. My lucky, Arrhenius relationship again. So I'm going to go ahead and start to define that. So K, I want it to make sure we're in joules, so 3.8 times 10 to the minus 23. And now we can look at this function. So diff, I'm going to call it diff equals d naught. Let's get d naught like this, times exponential minus qa divided by k times t. So this is our generic equation setup. So let's go ahead and see. I need to calculate the activation energy of Fe and V. So I don't know what my D naught is. I don't know what my QA is. I know from this plot I could figure out the diffusivity and temperature at some of these values. So let's do iron first. So I'm going to scroll down and I'm just going to do, again, these are not going to be the most accurate calculations, so I'm just going to go ahead and say, all right, around here, we're about 10 to the minus 13 meters squared per second. So that's my diffusivity. And I need another temperature because I need two equations because I have two unknowns. Let's see, where does this match up? Maybe something like this, 10 to the minus 16. So I know, for example, that for here, my diff, I need to solve two equations simultaneously. So I know my diff is equal to basically 10. And I need to actually, I need to plug in. So I need to do diff slash dot t goes to, let's see if this will allow me to do it. T goes to 900. We need to make sure that we're in Kelvin. So that's really, really important. So let's see if this gives us the nice values. So that is equal to 10 times 10 to the minus 13. And then I also need to solve diff. When we go down, I think it goes down to minus 16 meters squared per second, thankfully, 700. And then I want to solve for QA and D naught. And then I want to do the reals. Numerically solve. I may have messed this up. Oops. Yeah, let's go ahead. Let's let's see why we're getting this value or not getting the value we want. So I'm going to do solve. Yep, I need the values and I need the reals. So what is the problem there? Sometimes it doesn't like this expression. Yes, for some reason it's not liking this. What if we do this? Yes, so let's try this. And like this. Again, coding is just a lot of trial and error. And voila, we got it. Not too much trial and error. Fantastic. All right, so that is for Fe. Let's look at vanadium. And that's going to be a tough one. Mr. Steinmal, why did you limit yourself? But anyways, oh, shoot. So let's go to 900. So let's say that's about in between. So let's say it's like 5 times, say it's like 5 times 10 minus 16. So again, I'm just going to do the exact same here. But for 900, it's like, actually, let's see, 5 times 10 to the minus 5 times 10 to the minus 18. And then let's see, just a little bit further. So that's a 900. Say this is like 850. It's all the way down. Let's say at 850. Again, these are all approximate. I'm just looking that you're setting up the equation. It's 10 to the minus 18. And we got those values as well. So, excellent. So we figured out the activation energy. Now, I want to coat chromium with a layer of iron for a corrosion application. The layer must be at least 100 nanometers thick. This needs to happen in 5 hours. What temperature do you need to operate to make this happen? So I need to coat something. I just need a thickness. So my thickness is 100 nanometers. So I'm going to use my engineering approximation, which is 2 square root dt. My t is equal to 5 hours. So again, let's start to kind of figure this out. So layer must be, so my x depth equals 100 times 10 to the minus 9. What else? I need to finish it in 5 hours. So my temperature, my time is equal to, time t, this one, t1 I'm just going to say, is 5 hours times 60 minutes times 60 seconds. So I got that. So now I just need to figure out what diffusivity will work. So let's go ahead and let's just solve. Solve x depth equals 2 times square root of d times t1. And let's look at this numerically. So my diffusivity has to be at least 1 point, that's the lowest diffusivity, 1.38 times 10 to the minus 19th. And we're coating it with iron. So really, at any temperature, you could even get down to well below, any temperature, 700 will, make it work. So there's lots of answers that will work. Basically, any temperature, any realistic temperature on here. So anywhere from 900 to, heck, even well below 700. You could probably get to 600, but anyways. So excellent. All right. Instead, if we were to write out a solution of this concentration profile of Fe into chromium, which I neglected to make is 100 millimeters thick, write out the boundary conditions. What is your solution? And when would your solution be valid? You don't need to solve it explicitly. So in this problem, we're looking at I am looking at a material. So I have a block of chromium, which is 100 millimeters thick. So this looks to me like it could be semi-infinite, x equals 0. I'm spraying my iron here. I assume it's 100% iron. So if I'm looking at my iron, this obviously looks to be an infinite. So my boundary conditions would be my concentration of iron at an eta equal to 0. Again, I'm going to solve my ODE would be 1. My concentration of iron at an eta equals infinity would be 0. And as long as this L10 root dt is not violated, I'm good to go. There we go. All right. I'm interested in investigating the implantation of boron in silicon. I need a boron concentration of 1 times 10 to the 16th atoms per centimeter squared. So what is the activation energy of boron? So I need a boron concentration of 1 times 10 to the 16th. All right, so I need to be over here. And then I'm asking, what is the activation energy of boron? So I know I have this equation, d equals d naught exponential minus qa divided by kt. We solved that last time. But where's my diffusivity? I don't have it. But I could use this equation, square root 2t, in order to solve for first my diffusivity, and then I could figure out what is basically that activation energy. So I know the x depth that this is penetrating. So here, as implanted, so this is actually my starting point here. So as implanted, and then if I look at 90 C for 30 minutes, I get to a distance here. So I've traveled what it looks like to be half a micrometer. So I can start to solve for that. So let's go ahead and let's plug in. So let's look at x1, or let's say x at 950, 30 min. That's not, okay, so my distance traveled there is basically half 1 times 10, 0.5, yeah, 0.5 times 10 minus 6, half a micron. So I've got that. So what was my basically time here? So the time spent was, time is going to be equal to 30 minutes. So 30 times 60, that gives me everything in seconds. So I got my x, I got my t. I could solve for d now. So I'm going to solve for x 950, disgusting. Oh, I should do this as, I'm going to clear t for a second, because I don't want t. I'm going to call this t2. Usually I should name this in terms of the problems, but again, I know that you'll use more appropriate variables than I do. Plus, I'm always doing this on the fly. So let's look at d, again, to solve times t2. So that's my diffusivity. And we know that this diffusivity occurred at a very particular temperature. Now I want to repeat the same procedure, except for the clear, for a different distance. So because then I'll have two diffusivities, two different basically times or temperature conditions, and then I could solve for the rest. So let's go ahead and look at 950 for, let's stick at the same temperature. Actually, let's go ahead, let's look at 950 for 90 minutes. So now I can look at the diffusivity here. So let's look at this value. Or actually, we could even bump it up in terms of temperature. But we can kind of figure that out at a later point because we need that D naught. Actually, let's look at something a little bit easier. Let's look at here. Because from here to here, that's basically half a micron. And then another, basically, actually, let's see. Is that really half a micron? No, that was actually, excuse me. So that was like 0.25 microns. So sorry about that. 0.25 microns. So, all right. So there's my diffusivity at that particular time and temperature. So I also have a different diffusivity. Let's go ahead. It'd be nice if we could get the same time, but we're not really getting it in this problem. So I'm going to go into here. I'm going to look at what is this diffusivity. So let's do 1,000, or let's do actually this guy. So that's basically half a micron, and then so it's like 0.75 microns. So my x at 1,000 C (60 minutes) it's 0.75, and this is 90 minutes. So I'm going to call this T3. And let's do this. Plug in here. Let's do T3. Now this is my diffusivity here. So I'm going to now solve and actually pull out the same equation here. So now my diff, I could just plug this in for my diffusivity is equal to this at a temperature of 950 C, but we have to do 950 plus 273 equals that, and then I also get a temperature at 1,000 C, 1,000, and then my diffusivity is this. And again, it should make sense. My diffusivity here is 3 times 10 minus, it's getting lower, so I could actually take the ratio of this divided by this. So this is a bit larger diffusivity. But anyways, we'll go ahead and get these out. And then let's go ahead and solve. And we've got our values. Oops, actually 10 to the 19. Oh, excuse me. That's for 950. Actually, we did a little bit of mistake here. This 1000 plus 273. And there we go. Ooh, but there it looks like there's an error here. So let's go back. All right, I think we had 0.5 here, so let's rederive this. I see, here's the mistake. So again, that diffusivity should be lower. And we took the ratio now. It's 0.3, that makes more sense. All right, things are making a little bit more sense now. So let's go ahead and let's plug this in here. Let's get it over here. Now, what do you know? Much better. All right, so we've got our diffusivity, and actually we've got the activation energy, we've got our D naught, so we are good to go. Fantastic. So now let's look at my favorite problem. This will absolutely show up on an exam, and so let's go ahead and let's kind of write it out together. So I'm looking at Fe2O3. So this is my host, and this Ta2O5 is my impurity. So in order to change the band gap structure for electrical properties, I'm looking to dope. Fe2O3 can form cation Frankel defect, Schottky, blah blah blah. Activation energy for anion 3.2, activation energy for Frankel 7. So Schottky is the dominant defect. So when we look at intrinsic versus extrinsic defects, so I'm going to go ahead and do right now, basically 2 plots, T, 1 T, and I know that here, again, intrinsic dominates at high temperature, so intrinsic here, extrinsic here, extrinsic here. So extrinsic is going to dominate at lower temperatures, so higher values of this 1 over T. And we'll take the natural log. Let's see what material what are we interested in today. So I am interested, John label the concentration, Fe vacancies, and the diffusivity of Fe. So I'm going to look at the natural log of the concentration, vacancies, and Fe, which is 3, and then the diffusivity, natural log of the diffusivity. There we go. So let's start to write some reactions. So the Schottky defect. So my intrinsic defect is as follows. So my intrinsic defect is what? So null goes to vacancy of Fe, which is 3, plus vacancy in oxygen, which is 2. How am I going to charge balance this? 2, 3, good to go. So now, when I write this reaction, my K equilibrium, so basically if I look at this, we also have to do an electroneutrality statement as well. So remember, when I'm writing my electroneutrality statement, vacancy of Fe, concentration of this equals concentration of this, what do? We always put what? Our charge here. Does this make sense? So for example, if my concentration of vacancies of oxygen was 3, actually let's make it 5. So my concentration of vacancies of oxygen equals 5. So that equals 5. So now I have 5 times 2, so that is basically 10 positive charges. So 10 plus. So if this is 10, how do we work this out? So where's my, it's like 5 times 2, so I could bring this over. So 3 divided by 2, so I could do that. Let's basically look at here. So now the concentration of my vacancies in Fe, actually let's make it instead of 5, let's make it 6. So let's say my concentration vacancies of oxygen, let's say this equals 6. So 6 times 2 is going to be how many? So I've got 12 plus charges. So if this is 6, 12, if I divide that over, what does that equal? So my Fe3 is going to be equal to what? 12 divided by 3 is 4. So 4 of these times 3 is going to give me what? What charge? Or actually, it's not 3 times 3, excuse me. And my concentration of vacancies here, what is it equal to? So I have 4 of these, so I had 6 of these, so I had 2 of these. So that was plus 12. So 4 times what's my negative charge? 3. So that's 12 minus. So again, always put that other charge there first. So don't worry about these exponents here. If you're in charge neutrality, forget about that. Now, if I look at my equilibrium with my Schottky, so that is going to be Fe, you can see it F3. Now remember, this goes squared times vacancy of oxygen to the cube equals exponential minus G formation of Schottky over KT. Great. So I'm going to use this electroneutrality equation because I need to write everything in terms of the concentration of vacancies in my iron. So I'm just going to go ahead and plug that in. So now my basically concentration vacancies of Fe23 squared times, now this is going to be 2, let's go ahead and plug that in here. It is going to be 2, actually 3 over 2. 3 over 2 concentration vacancies in Fe3 cubed equals exponential minus G formation of Schottky over KT. So now I don't really care. I'm looking at I'm going to be looking at the slope. So realistically, again, don't be confused about this too much mechanically. Vacancies of Fe scales as to the 5th, so proportional to exponential minus G formation of Schottky over KT. So when I take the natural log of this and the natural log of this, exponential disappears. Where does the 5 go? Actually, before I even take the natural log, excuse me. So before I take the natural log, I want to, this is to the 5th, I want to get rid of this exponent. I'm going to solve for the log of concentration of this. So if I want to get rid of this exponent, I'm just going to put it right here, 5. Now I'm going to take the natural log of this, natural log, this disappears. So again, I have this Arrhenius relationship. My y equals some slope m on 1 over t. So my slope is what? Exponential's gone away because the natural log minus GFS over 5. Okay. So my slope here is minus G formation of Schottky over 5. Okay. There we go. So what about my diffusivity? Well, I know that my diffusivity is proportional to my hopping attempt, my R squared, my F times my concentration vacancies in Fe, because that's how my Fe diffuses, all over 2 dimensionality. Dimensionality is just 3, doesn't vary with temperature, F doesn't vary with temperature, R doesn't vary with temperature. My hopping frequency, that is proportional to exponential minus G migration over KT. So when I multiply those values, we already have this relationship here. So this is going to have a slope as well, or actually a slope over here, excuse me. So again, we're still in the intrinsic regime, so I'm looking at diffusivity. So this is going to be minus G formation of Schottky over 5K minus GM. That's it. Now, extrinsic defects. So let's kind of get into that. There we go, there we go, there we go. We're writing, we're writing, we're writing. Fantastic. Okay, so I look at these defects. It's very, very important. So I'm going to dope Ta205 into my host. So my host is Fe2O3 because it has all those Schottky defects. So Fe2O3. So the first thing I know is I need to create vacancies in Fe. So that's 2, 3. So I'm going to do substitutional cation. I need to. TaFe. So what is that? Fe is 3 plus tantalum 5. So I'm going to do 1, 2. So that's a change in charge. So how can I charge balance this 2 here? I don't like that. How am I going to work this out? Let's go ahead. Let's do something like this. Let's say I want to do 2 here. I need to do more than 2. So let's say I do, What is 4 times 2 is 8? No, that's not going to work. Ugh, do I want to do 6, 12, 4? Ugh, ugly, but it'll work. So let's do mass balance. So I've got 6 TA, so I need 15 oxygen. 15 OOX. All right, that'll work. What about for my Fe? 4 Fe. Actually, I need 10 Fe. Oof. So 5 and then 15. I'm good to go. So I just need my charge balance because I don't have this chemical equation there. So vacancy of Fe, 1, 2, 3. Again, what do I move down? The charge. And then Ta, Fe, 2. What do I move down? Charge. Again, let's do that one more time. So if I have, let's say, again, let's do 6. So if I have 6 Fe equals 6. So then I know that charge from that is going to be 12 plus. So looking at this over here, so this is 6, that's 12, so that means the concentration there is 4. Okay, we got it again. All right, fantastic. So I know in the extrinsic regime, we're at very, very low temperatures. So that exponential, exponential relationship is not going to dominate. So the extrinsic relation dominates, and then here we can see a direct correlation between what we create in terms of these defects, this extrinsic defect, and then how it affects our Fe. And we see that there's no temperature relationship here. So the slope for how does the concentration vary, it's just basically 0 here. And you would just directly relate it to this guy. When I'm looking at diffusivity, I still have this following relationship that holds. So I'm still proportional to this, but the only term that comes up is that minus Gm over K. I'm talking about diffusivity. And there we go. That's your diagram. And that is problem set 4. So I hope you do well on this one. One more problem set to go, and then we're getting ready for the exam. So study hard and keep doing well. 5 out of 8 problem sets are going to be done. So you're in for a little bit of a break, well-deserved break. So I'll see you in the next video. Thanks.